Okay, this is for the advanced students. We're going to go through calculation of these a little bit more advanced problems. I think the first thing you need to notice is this part here, which would indicate, since it's in grams, that is an ideal gas law problem. You're trying to find the mass of this. So if we're going to find the mass, we're going to use this part, but it's going to be at the very end. Our target is going to the mole. I'm going to have to use these factors here in order to figure that out. Since these are in different units than atmospheres, we can kind of work on changing these. My standard unit for torr, or my standard for that, would be dividing that by that, and it would get it into atmospheres. So all you have to do is just use your calculator and just pop these in really quickly. So this one would be actually 1.97 atmospheres. We'll set up our formula down at the bottom. And this is going to be 0.0821 all the time with atmospheres. That will be my first standard number, which goes here for the pressure. Now we're going to go with my volume, which is my next given, and we're going to divide that by 1,000. Because it can't be milliliters, it's got to be liters. Now we could use this as a conversion chart, but it really isn't necessary, since we already know that if we're going to convert to another unit that we want to hit, we're going to be dividing. So on this one here, that will go here. We are solving for the number of moles. We have to convert this one by adding 273 to get the Kelvin. So it's going to be 515 plus 273, and it's going to be 788 Kelvin, which will go here. Now we got all the numbers in, which is really nice. We're going to solve, so I'm just going to go 1.97 times 0.395, and I got 0.778. And then on the other side, I got 0.0821 times 788, which is 64.69. I won't worry about the rounding, but if you want to be a little bit more specific, we can put a 5 there. And now we're just going to solve out the last part using algebra. And what we have for our number of moles is 0.778 divided by 64.695. And I got 0.012 moles. Now with this one, it's kind of a clever setup. We are trying to find the mass. If it's giving you something like this, we already know our mole number. We also already know our gram number. So we're going to go with this, divided by the 0.012 moles. And that will give me my mass. And my mass is going to come out as 32 grams. So if you take a look at your sheet, it does give you the answer here. We still would apply that to grams per mole. My gas that's going to be at it, which is the gas. Remember, you got those diatomic gases. So we got BrINClHF, or Brinkelhoff. We'll see, make sure it's on there. So those are my diatomic gases. And we got our numbers here. I'm going to stick it down a little bit so you can kind of see it. Again, make sure to go through process. We got 32 grams per mole. We know if we divide this by 2, we can take into account that my mass of that element is going to be 16. So my gas is going to be oxygen gas. There is a lot of parts on this, but again, it is a very workable problem. The moral of the story is you're always going to have to go to the mole, especially when you have grams. Now let's go on to the next question. Keeping into account time. And again, if it's off the screen, I am sorry. That was a little bit more work. I will make sure to fit this in here, but what is the density of oxygen gas at STP? There are 2 different ways actually to do this. But first of all, we'll do the PV equals nRT, because we could have different factors here. And if I look at it, density, grams per liter, mole. Again, moral of the story, go to the mole. Now, standard temperature is going to be what's added to get to Kelvin, which is going to be 273. My R is going to be 0.0821. My pressure, standard pressure, is 1 atmosphere. Very good to stay into that. And my volume is going to be coming from the density part, which is 1 liter. That is 1, and then N, and you'll see an amazing number, which is 22.4. 1 divided by 22.4 is 0.0446, which is my moles. Now I have to convert this to my grams, oxygen gas, again part of that Br2, I2, N2, Cl2, H2, O2, F2, Brinkelhoff. Make sure it's on there. It's not, but we got our bromine, iodine, nitrogen, Cl, chlorine, hydrogen, fluorine, Brinkelhoff. Now I just have to convert it and get to the grams at the top because I already have the part on the bottom. So I'm going to go mole, mole, mass. That's where it's coming from. Big unit, smaller unit. And then all I have to do is just multiply these together. You will see that it'll come out as 1.43 grams per liter. Or there actually isn't any other way to kind of do this, but we're good on this. That is my answer, 1.43 grams per liter. My last one I'm going to do is actually one of the Graham's laws. And these are some of the sentences that you're going to see. How many times slower does radon move than nitrogen gas? So we got 222 grams, which is off the periodic table. We got nitrogen gas, which is part of that BrINClF. Brinkelhoff. And we can do our mass of nitrogen, which is going to be 14 times 2, which is 28. I have my 2 mass numbers because if we're talking about how many times slower somebody runs or how many times faster, we're going to do it according to their mass. So we're going to have 222, and we're always going to put the higher number at the top because it really doesn't make sense to go, well, somebody runs half time slower than somebody else. We don't want to do that. We got 7.93. That's kind of a hint that we're not doing it correctly. We did it correctly. We just have one more step because in chemistry we always go an additional step. And we now have to do the square root of this, which is the same answer as what we get here. So radon moves 2.82 times slower than nitrogen gas, but by the same virtue, nitrogen gas moves 2.82 times faster than radon gas.